We're now going to talk about yet another type of scheduler that you can use together with reactive types in Project Reactor. If you recall, we've talked about various schedules. We talked about the parallel scheduler, we talked about single-threaded scheduler, and now we're going to talk about a scheduler called bounded elastic. And the idea of bounded elastic is to be able to use this with either the flat map concurrency idiom or, in this case, parallel fluxes, in order to be able to do I/O operations where the pool can grow up to some bounded amount. Not surprisingly, bounded elastic also works with fluxes and monos, as well as parallel fluxes. So let's take a look at how this works. So the bounded elastic operator will create a bounded number of executor service-based workers that can be created dynamically, and it returns a new scheduler that's suited for I/O bound work. Remember, the parallel scheduler is not intended for I/O bound work. It's only intended for CPU bound or computation intensive work. And why this works for I/O bound work, why bounded elastic works for I/O bound work, is because the implementation can dynamically add or remove threads from the pool depending on whether or not some threads are blocking on I/O, and we need more threads in order to keep the computation moving forward. So it's optimized for blocking tasks, unlike the other thread pools which are not optimized for blocking tasks. In particular, parallel is not optimized for blocking tasks, it's for non-blocking tasks. As we've talked about before, blocking tasks can benefit from more threads, whereas CPU-bound tasks can't. Because if you have only 4 cores or 8 cores or whatever, and you've got all your threads, all 4 of your threads or all 8 of your threads humming away, having more threads doesn't help because they won't be doing anything because they're not blocking. They're CPU intensive. Whereas I/O-bound tasks can benefit because while one thread's blocked, another thread can be brought up dynamically or pulled out of a cache in order to be able to keep things humming along. The way that bounded elastic works is when you have a next piece of work to be done. If there's an idle thread that's sitting around in the cache, it will be reused. If there is no idle thread, then a new thread will be started up to some limit. And if the threads that are in the cache go unused for more than 60 seconds, for more than a minute, then they will be evicted and destroyed. So this is trying not to just create threads willy-nilly. It creates them only as long as they're needed and then recycle them. So the goal here is to be able to maximally utilize CPU cores. The max number of created threads is bounded by a cap, and by default, this cap is 10 times the number of available CPU cores. I don't know whether there's a way to address that. And basically, there's also some bounding on the amount of queuing that can take place. So it's a bounded elastic. It's not an unbounded elastic implementation. This type of thread pool, the bounded elastic pool, is particularly useful for things that involve I/O, network calls, file I/O, database operations. Here's a simple example that we'll take a look at later, where we're going to be downloading images from some servers, and we're going to do it in parallel, and then we're going to take the results and collect it into a list and do something with the results. The implementation of bounded elastic is done via so-called daemon threads. And if you recall from our earlier discussions, daemon threads are designed so if there's no more user-level threads and only daemon threads, like only bounded elastic threads, the process will shut down. If there is at least one user thread around, then the process will not shut down. So the way to think about this is when you use bounded elastic, you don't have to close anything down in order for your application process to exit gracefully when it's done with whatever it's doing. There's an operator in RxJava called schedulers IO, which is very similar. It's also intended for blocking operations. And the Java common fork join pool is also very similar, especially when you use it in conjunction with managed blocking, which is a feature that's available with the common fork join pool. So let's now take a look at how to program with schedulers bounded elastic. This particular example can be found in the EX5 project in my Reactive Flux folder in my Live Lessons GitHub repository. And it downloads images from remote web servers in parallel and stores them on the local computer's file system. As you can see here, the first thing we do is we call a factory method to create a flux that contains URLs to be downloaded from these remote web servers. We then convert the flux to a parallel flux by calling the parallel factory method. Notice there's no parameters passed here, so it'll default to the number of cores available on the platform. Next, we call the run-on method, passing in the bounded elastic scheduler that's obtained from the scheduler's bounded elastic factory method. And this is an I/O-based scheduler that can download and store each image in parallel. At that point, we call the map operator, defined on parallel flux, to download and store each of the images in parallel. We then call the sequential method, which will merge the values from each rail in a round-robin fashion and then expose it as a regular flux sequence, from which we can then call the collect list method to collect the flux into a good old Java list. And then finally, we'll handle the final results that have been downloaded and stored, and we'll go ahead and print out the results through some kind of logging mechanism using the do-on-success action operator. So that's the end of this particular discussion about the bounded elastic scheduler that's defined for a range of Project Reactor reactive types. We focused here, of course, primarily on parallel flux usage of this scheduler.